Hey, welcome back, everybody. Hope you had a good week. Before we proceed, just a couple of comments and then we'll continue. Number one, we're about halfway through. Spring break is coming up here pretty soon. I think we're in our 6th week here. So the point that being that if you need help, okay, now's the time to get help, okay, because we are building on information that we're going to use throughout the remaining chapters. Now, we do have, SCC does offer, obviously, tutoring services. You can access that. You can email me. Normally adjuncts are not required to have office hours. I do have them when we're on campus, but if you need time, or email me, we'll set up a time to do a Zoom. We can go over whatever problems you need to discuss. Okay, so we are available. I am available. And then the other aspect too is, as I mentioned way back when in the beginning, is I teach the same class, same textbook to GCC, and I meet there on Tuesdays and Thursdays through Zoom, starting at 3 o'clock, 3 to 4:15. You guys are a little bit ahead of that group, but that's also an opportunity to get another hit on the information. Okay, so you're more than welcome, same link to jump in there and visit my GCC class. Okay, I'm trying to find out if I can have the GCC students or SCC use the GCC's tutoring service. I don't see a problem because, you know, if you can't get to the one at SCC, one should be able to go access the GCC. I mean, it's online, you can click it and get information. I'm sure they're more than happy to help. And like I said, I'm here too, so don't forget that. Okay. The session we did the last couple of Fridays, remember that I just assigned the videos that were pre-done, and it was the last 2 Fridays because I had some personal matters to take care of. That was just temporary, okay? That was not a permanent. We're back to the regular time. I see the majority of you are here at 12, but those days were just temporary. Also, I did offer the class at a later time, and it also recorded it like normal. So if you couldn't make it at the later time, you obviously can view it on the YouTube channel. So, you know, that's not a permanent. Somehow there was miscommunication, and there was information sent out saying that I changed the time for this class. I'm not authorized to do that. I can do a little bit if something like that pops up, but not permanently, okay? You signed up for 12 o'clock, and that's what you get. All right, any questions? And one last statement. Does everybody know where you get your resources, where you get the textbook, where you get everything, okay? I state that because in the past I've had that, people not knowing where to get the information, okay? So just to double check. Any questions, comments, concerns?
I have a quick question. I did the lab midterm just before class, and I realized I read the question wrong as like the formatting for how it wanted, like say it wanted the units and then it wanted the digits and then the units together without a space. And I put the space in between that. Is that something I should email you about?
Yeah, okay. Exactly. Anything like that, the answer is correct, and you're not going to be taking points off if you added a space or an extra space, simply because Canvas is not an AI type of software. It doesn't. If you add a space or by inadvertently add a point, a decimal point, or you add an extra space, Canvas treats it because it counts each character, including the space, and checks the answer. And if it doesn't match it exactly, it counts as wrong. Well, you know, we're trying to teach it of all the other options that people can put an answer in that are correct. And that list gets longer and longer. So yes, if you added, typed in an answer in Canvas, you know it's 100% correct. Canvas says, okay, you're wrong. Now, send me an email. Please tell me which assignment and which number, because everybody's right now is kind of spread out, and definitely give you credit for it. That also goes is true for any images. Tech Support has been working on this since we started this online business. There's some reason Canvas, for some people, they see an image, other people, they don't see an image. And it's not, there's no rhyme or reason. It could be with this question, that question, any multiple things. So if you ever have a question and ask you to look at the image and you don't see an image, I honestly have to give you credit for that. No problems. Again, just let me know which assignment and which number, and we'll take care of it. Okay.
Thank you.
No problem. All right. Any other comments? All right. Okay. Well, we ended up in chapter 8, which we're dealing with nomenclature, and that's naming compounds. We're going to you're going to be in a position where you're given the formula, and then you're asked to give the name, or vice versa. Okay. Which again brings me to the point about the nomenclature exam, quiz, whatever you want to call it. It's unique to SCC. The department requires this exam as a separate entity, and there's only like 20 questions of give the name or give the formula, and the SCC department requires a 80% passing to give you the points. So anything below 80%, Canvas kicks it back to 0. And so you can continue to repeat it. You have an unlimited number of attempts. And some people have got their 80 and they're happy with that and move on. And others have continued to repeat it until they get maybe higher. It's worth 10% of your grade. And I can tell you this, and this basically the only thing I can tell you is that if you're on the border with respect to your grade, it can knock you off that border and bring you down at 10%, or it can kick you up to the next level. Okay. So your decision, your education, I recommend, taking it. If you're happy with the 80, then, there you go. So any questions on that? All right. Well, let's continue with chapter 8. Let me share my screen and let me back it up a little bit, one page, just to refresh your memory. We were talking about, one second. We were writing formulas for ionic compounds, okay? Remember, ionic compounds, combination of a metal and a nonmetal. So we had this example here of sodium and sulfur, and they're going to present it to you like this, okay? Well, what you got to do, since we're talking about ionic compounds, is step number 1 is convert those atoms right here, sodium, into their respective ionic form. So that means that you have to be aware of where it's at on the periodic table, because it's going to tell you what kind of oxidation number or charge it's going to have. If it's a metal, here's the thing that people are forgetting. All metals, okay, lose electrons and end up with a positive charge. They're called cations. All nonmetals gain electrons. The driving force in both directions is by gaining electrons for nonmetals. Now it fulfills the octet. It fills up those empty spots where electrons can occupy, and you end up with 8 electrons on the outermost shell, the valence shell, okay? So they become isoelectronic with the noble gas in front of it. Now we're talking about simply about the A metals, 1A through 7A. All nonmetals, okay, will lose electrons. And by losing electrons, they now have the next shell in is full with 8 electrons, and they have their octet fulfilled. So in both cases, losing and gaining electrons, they're going to have the octet fulfilled, okay? All right, so sodium is in group 1 element. meaning it got one valence electron. So in ionic form, it becomes a positive, okay? Always a positive, it's a metal. Sulfur is a nonmetal, and sulfur is in group 6. And being in group 6, it's going to gain electrons because now it just simply needs to pick up 2 electrons and now has 8, a total of 8. And by picking up 2 electrons now, it has a -2 charge. Okay, so we put the atoms into ionic form, which we have right here. Now we put them together to write a formula, and we write them such that we have enough positives and enough negatives to cancel each other out. So when we put them together, we have a net 0. So we need 2 sodium ions because that gives us a total of +2, which cancels out the -2 of the sulfide. Okay, so this 2 now becomes the subscript for sodium. So that is the formula for sodium sulfite. Okay, notice, remember, refresh your memory, the nonmetals change the name. The single nonmetals like sulfur, oxygen, nitrogen, all the halides, fluorine, chlorine, they start off with the atom name, but you take out the last 3 letters and add the IDE. So sulfur becomes sulfide, chlorine becomes chloride, etc. Okay. All right, so systematic approach, converted to ions, and then that allows you to put them together in the proper ratio. They will come together either as a 1-to-1 or a 2-to-1 or 2-to-3, any combination of whole numbers such that they have a net 0 positive charge. This is a net 0 charge, excuse me. Okay, magnesium. Magnesium is a group 2 metal. Being a group 2A metal, it will lose 2 electrons. Okay, those 2 valence electrons will go away, resulting in a +2 charge for the ion of magnesium. Oxygen, like sulfur, is in group 6A. It's a nonmetal. It will pick up 2 electrons, resulting in a -2 charge. So now I have the +2 of magnesium ion and oxygen in its ionic form, now called oxide. Okay, so I can put them together on a 1-to-1 ratio. That means that my formula will be as follows. Okay, so that is MgO. Not necessary to put the subscript of 1. It's like in algebra mathematics. If it's 1, it's just simply 1. You don't have to put a 1 any place. Okay. Next one, we have potassium and we have phosphorus. So potassium, group 1A, like sodium, so it also has a +1 charge. It is the metal. We lose that 1 valence electron. The phosphorus, okay, phosphorus is a group 5A nonmetal. So it will pick up 3 electrons because it has 5 in the valence shell, so it has room for 3 more. Okay, from an energy perspective, if you think about it, phosphorus has 5 valence electrons. And to get rid of 5 versus adding 3, well, energy, relatively speaking, it takes less energy to add 3 electrons, plus now it has the octet and therefore a lot more stable than trying to remove 5 electrons and then try to get the new octet. Just from energy perspective, not very efficient to lose 5, pick up 3 because it's a nonmetal. Okay. Yeah, okay, so now we need 3 potassiums, 3 potassium ions to cancel out the phosphide -3 charge. So that 3 becomes the subscript for potassium phosphide. We'll get to all the names here in a second. So its formula will be K3P. Okay? This is a rehash of what we finished up last week. We have calcium and nitrogen. Okay, so calcium is a group 2 metal. It will lose 2 electrons. Nitrogen, like phosphorus, is a group 5A nonmetal. It will pick up 3 electrons like phosphorus just did. Okay, both share, they're in the same group. Okay, so that nitrogen now becomes nitride with respect to the name. Now, the previous examples 1 through 3 is fairly straightforward. Like it's either 1-to-1 or 2-to-1, you know, straightforward. But here, not so straightforward because we got calcium with a +2, and we have the nitride with a -3. So I can't put them together as a 1-to-1, okay? Because I'm going to have, if I put them together as 1-to-1, I'm going to have a net -1 because the +2 and then 2 of the negatives will cancel out, but leaves us with a -1. So that won't work. So what I have to do here is I have to find a common number. Just like we do with fractions, we're going to add 1/4 plus 1/5. We kind of find the lowest common denominator. And here we're finding the lowest common number. Generally, all you got to do is just multiply these two numbers. 2 times 3 is 6. So our common number would be 6. So I need to add enough calciums to give me a 6. Specifically, if I multiply by, if I use 3 calciums, I'm going to have a total of a +6 charge because each potassium, I keep calling it potassium, each calcium has a +2, okay? We do the same thing with the nitride, and here in this case, we just need 2 nitrides because 2 times -3 gives me a total of -6, okay? And so that equals to 0, and that's what I need. Okay, so those numbers now that I put in front of the ions becomes the subscript. So our formula becomes calcium subscript 3, nitride subscript 2. Okay, and that is our formula. Now, it's a little kind of a hint for you if you recognize this. Think about this for a moment. The 2 of the nitride, wasn't that the charge of the ion, right? And the 3 on the calcium, wasn't that the charge of the nitride? So, you know, that may give you a little hint. If you don't see it, don't just go with what I just did here, find a common number. And then when you later on, the more you do, you hopefully pick up on that. Okay, so putting that together, our formula becomes C8 subscript 3 and 2. Okay. Now, aluminum is a metal, obviously, right? And it's in group 3, and therefore it will lose those 3 electrons, resulting in a +3 charge for that ion. Okay. The chlorides are nonmetals in group 7. They just need 1 electron to fulfill the octet. So they end up all halides. Everybody in group 7, when they become ions, have a -1. So to put these together, you can see that I need 3 of the chlorides for every aluminum ion. Okay, so we end up with a formula of AlCl3, aluminum chloride. Zinc has a +2. It is one of those sweet 16. Remember those 16 atoms that we know 100% of the time in their oxidation state, their charge? Zinc is one of them, okay, had a +2. And the iodide, like the chloride, is a -1 to group 7. So in this scenario, I just need 2 iodides for every 1 zinc ion. So that gives us a formula of ZnI2. Okay. Now you might be tempted to think, oh, wait a minute, let's take a look at this. I see ZnI2, and I want to think diatomic, okay? Because I2, well, it's not, okay? In this form, when there's a metal written first, followed by whatever halogen, and there's a 2, not diatomic at all. It is telling you that the zinc is the central atom, which is the way the format normally is written, is the metal written first, followed by the non-metal. And then we got 2 iodides attached to the zinc ion. Okay, so it's not diatomic iodine. Okay, now, another factor here, which people kind of get confused with, is that Roman numeral. Remember that Roman numeral are for those metals that don't belong to the 16 group. okay? The 16 group, those are single oxidation states, single charges. They're always like that 100%, which means all the other metals, their oxidation state can vary, okay? And you have to be told which oxidation state you're working with, or you have to calculate it. And we're going to have some examples of how to do that, okay? Because you're always going to know the oxidation state of either the cation or the anion. And they're realizing that they're going to equal 0, you can calculate one or the other, okay? So here we're dealing with copper +2, and that is denoted by that Roman numeral. So we're dealing with this ion, copper ion, because we have to do that because there's also exists copper 1 with a +1 charge, and we have to distinguish the two by using Roman numerals. And then the oxygen, like up here, has a -2 charge. So we have, formula-wise, we can put them together as a 1-to-1. And it gives the following formula. Here's another one with a variable charge metal, which is Pb, which is lead, okay? Roman numeral 4 tells us we're dealing with lead +4. The oxygen, again, now is still oxide, a -2. And to put these together, I need 2 oxides for every lead +4 ion. So my formula becomes PbO subscript 2. That is my formula. Okay. Now, to write the names out of these, we got sodium. The metal name doesn't change, it becomes sodium. Sodium remains sodium. To distinguish between the sodium atom, or we use the word atom or ion to distinguish one over the other. Whereas the non-metal, its name changes. So sulfur now became sulfide. Sodium, IDE, sulfide. Magnesium, oxide. Oxygen became oxide, okay? Potassium, phosphide. Went from phosphorus to phosphide, okay? Then we have aluminum, chloride, went from chlorine to chloride. Notice the trend here, IDE, IDE all the way around. The IDE should tell you, alert you to the fact that we're dealing with sulfur, but the IDE tells you we're dealing with just sulfur by itself, okay? Like sulfur, oxygen, oxide by itself. Down the road, with the next page, we're going to have things like sulfate. Okay, sulfate. The ATE tells you that we're dealing with sulfur, and the sulfur for SUL, pH for sulfur, but the ATE tells you that we have oxygens bonded to the sulfur to give you this polyatomic ion, and this is where you get sulfate. Sulfite. All right, that's chloride. Then we got zinc, iodide. Okay, now for these variable number 7, since we're dealing with copper and it's Roman numeral 2, we write copper, Roman numeral 2, oxide. Okay. And then the next one would be lead. Don't forget the Roman numeral 4, oxide. Now, here's another thing to watch out for when we're doing Canvas. Canvas, if you put a space between parentheses and say the R of copper in parentheses, or now put a space, I think we've been going through them and making sure that Canvas understands, but you get credit. It doesn't make a difference. You put no space or space. So when you If you write it correctly and you get counted wrong, let me know again which one it is. We'll definitely give you the credit and fix that, Canvas as far as their answer is concerned. Okay, notice that for the first 6, no Roman numerals, okay? No, we didn't say sodium Roman numeral 1, okay? Just simply sodium, because again, those are part of the column of sweet 16. They have that charge 100% of the time. We don't have to distinguish between any other types of sodium. There's only one type plus 1 sodium, okay? All right, now, FYI, you can start building your database of writing compounds, because yes, we did sodium and sulfur, but you know what? You can do sodium and oxide, sodium and phosphide, sodium and the nitride, and obviously the chloride and the iodide, and we're back to the oxide. And you can do that for for magnesium. Okay, start mixing and matching. So you have quite a database of compounds that you can put together now. Quite a bit, okay? All right, so any questions at this point? All right, so when you put together for ionic compounds, okay, when you put them together with respect to their charges, check to make sure that they equal 0. Now, let's say, for example, you didn't know what the charge was of a metal. And let's do a quick one. We're doing the copper one. As I stated earlier, I said there's 2 types of copper, copper 1 and copper 2, okay? So if you're given a formula, let's say you got copper, CuCl. The question is, what is the oxidation number of this particular copper? Well, what is it that we know? We know the chlorides always have a -1, okay? And we know that this whole charge has to equal 0. And so what we can do now is create a very simple algebraic equation where copper minus 1 is equal to 0. We saw for copper, and it stands to reason that copper in this state has to be a +1, okay? Yeah, that works. So now that means that we're dealing with copper, name-wise, Roman numeral 1. If we do the same for copper, this copper, well, we got Cu, okay, -2, because each chloride is a -1, so you got -2, and that equals 0. That tells me that Cu is equal to a +2. So in this case, we're dealing with copper, Roman numeral 2. And that is what I mean by, you're going to always know the oxidation number, the charge of either the cation or the anion, okay? And that will help you out to determine which one you're working with. In this case, copper 1, copper 2. All right. Now, for polyatomic ions, well, let me direct you to the periodic table. In the periodic table, in the bottom left corner, we have a table within the table here called the most common polyatomic ions, okay? And this is by no means an overall, all of the polyatomic ions that exist, but these are the most common ones that we're going to utilize at Chem 130. All right, the takeaway from this is the following. These are 1 unit. These are packets. Like, okay, we talked about this when we did the Lewis dot structures of these polyatomic ions. And so whenever we need to show that we need more than 1 of these packets or units, we use parentheses in our formula. And then we do a subscript outside the parentheses to tell us that we need 2 or higher. If you only need 1, there's no need for parentheses. You don't put a parentheses in it, okay? And so if we look at this, earlier I talked naming is very crucial, because that tells you what you're working with. For example, let me do this, it'll be better. going to work with the nitrogen. Okay, so obviously I have nitrogen, the element nitrogen, right? Now, when the element becomes an ion, nitrogen will pick up 3 electrons, so its name becomes nitride. Okay, so if you're given a name like sodium nitride, that tells you you have one dealing with the single element, in this case, nitrogen. Now, earlier I said these nitrogen can attach itself to oxygens to form these polyatomic ions, and they end up with a -1 charge. The whole unit, it's a -1 right there. I circled -1. That whole unit has a -1 charge, okay? And it has its own specific name, and that is called the nitrate, okay? And if we have one that has 1 less oxygen, then that becomes nitrite. Now, in the module in the chemist course that deals with nomenclature, I have uploaded some additional resources that comes into play when we're talking about naming these polyoxy compounds, okay? And what's the process? I'm going to go through that here in a bit. And so here we have what they all have in common in this scenario is they all have nitrogen, but different forms. Okay, the element nitrogen's up here, and then when it becomes the ion, it is a nitride, and then when it's bonded to oxygen, either 3 or 2 in this scenario, it becomes nitrate and nitrite. And that is the name for that unit. We don't change it to nitrogen trioxide or some crazy name. I think the whole thing is called nitrate. The same is true or similar if we use sulfur. Okay, we got, oh, excuse me. That's not sulfur. We have S, which is sulfur. Okay, and it becomes ionic, it becomes sulfide. Okay, and when it gets bonded to oxygen, specifically 4 of them, this becomes sulfate. And 1 less oxygen, notice it's a -2 charge. 1 less oxygen, same charge, it becomes sulfite. Okay, so the name, again, I can't overemphasize to look at the name, because you could be given, write the formula for sodium sulfate, okay? Or write the formula for sodium sulfite, or sulfite, or sodium sulfite, okay? All right, let's go back. Okay, so here we have magnesium, and then you have a OH negative. Okay, well, the fact that we got more than 2 elements in there and a negative charge should indicate to you, I got a polyatomic ion. Specifically, if you're not sure which one it is, then go to the table, and here it is. Hydroxide, that is its name, hydroxide. Very important polyatomic ion. We use that. We're going to use that quite a bit in the next chapter dealing with acids and bases. Okay, so that is the hydroxide ion. We do the same thing like we just did earlier. We take the magnesium, we need to convert that to ionic form. Find it in the product table, realize it is a group 2 metal, therefore it will lose 2 of those valence electrons and end up with a +2 charge. And then that OH is given to you, OH minus, okay? So now we're gonna put these together, and I need 2 of the hydroxides, okay? Because each one's got a -1. I need to counter the +2 coming from the magnesium. So what that tells me, since I'm going to need more than one, I'm going to need a parentheses. So Mg parentheses OH and parentheses subscript 2. That tells me I have 2 hydroxide ions for every 1 magnesium ion. And that is the formula. Okay, similar situation here. We got potassium, we did earlier, has a +1 charge, group 1A metal. Here we got the PO4 -3. Again, you're not sure what it is, but what should trigger something for you to look in the polyatomic ion is that this whole thing has a charge. So you go over to the polyatomic ion, look for PO4 -3, and there it is, right there. Okay, and it has, its name is phosphate. Okay, so you identified it, takes you back to the formula you're trying to create. And so we have potassium with a +1, again, group 1, A metal, PO4 -3, okay? I put -3 or you put 3 negative, makes no difference, it's the same thing, okay? Tomato, tomato, same thing. All right, so this tells me I need 3 potassium ions. So that 3 becomes my subscript 4, potassium 3, PO4. Notice there's no parentheses around the PO4, the phosphate, because I only need 1, okay? There's the formula. All right, here we go with SO4. If you look that up, you'll find it to be the sulfate. Silver is one of the 16, so always has a +1. There's a sulfate with a -2. That tells me I need 2 silver ions. So that becomes Ag2SO4. Formula-wise. All right. Calcium is a +2 ion. And then we have the nitrates, NO3 -1. And we need 2 of them. So again, we need the parentheses around the NO3 because we need 2 of them. And so our formula becomes Ca parentheses NO3 and parentheses subscript 2. And now we're using the variable oxidation state metals like copper 2. And we have Cu +2. And then this is the carbonate, -2. So here I can put them simply 1 to 1 because I got +2 and a -2. They cancel each other out. So the formula is as follows. All right, so remember with respect to the polyatomic ions, they use parentheses around the polyatomic ions if you need more than one, like in the case of hydroxide. In this case, we have magnesium, name-wise, so this would be magnesium hydroxide. Okay, then we have potassium phosphate. If you ever read your labels of what you're ingesting, you probably find a lot of potassium phosphate in there. This is silver sulfate. Okay, and then we got calcium nitrate. And then here, the last one, because we're using the Roman numeral here, it is copper, Roman numeral 2, carbonate. Okay. And as the previous case, you can do a mix and match. You can mix up the magnesium with the phosphate, or the sulfate, or the nitrate, or the carbonate. And the potassium is the same thing, potassium hydroxide, potassium sulfate, potassium nitrate, potassium carbonate, so on and so forth. So again, you're starting to build up your database. You should be maybe up to a couple, 300-400 different compounds by now. Okay. Any questions at this point? Okay, because right now we've been writing formulas. So the key takeaway from here is to write the formula, put them all in ionic form, then put them together with the correct number of each, cation and anion, so they equal 0. Okay. All right, so let's talk about naming them. Okay. So the name depends on whether the metal is a fixed or variable charge. Okay. And you might say, well, let me rehash for a second just to refresh your memory. Okay, if you recall, these, the ones I have in circle, are the metals that have a fixed charge. Everybody in group 1, with the exception of hydrogen, because hydrogen is not a metal. Okay, everybody in group 2A, and respectively, they're going to have a +1. Everybody in group 1 will always have a +1. Everybody in group 2A will always have a +2. Okay, and then the other 4, that's, that's 12 right there, 12 metals. And then the other 4, starting with aluminum, number 13, always has a +3. Zinc always has a +2. Silver always has a +1, and cadmium always has a +2. And that is the sweet 16, as I call it. So when you name compounds that contain these 16, no Roman numerals. Okay. That's the important part. So that means that everybody else here, whatever other metals you're using, you will be using the Roman numerals. And if you don't know what the Roman numeral is, in that example I did with copper chloride, you'll always know the oxidation number of the anion, and you can calculate the oxidation state of any of these metals. Okay? For example, I'm going to make up some hypothetical ones. Let me see. If I have a hypothetical M for metal, and it is bonded to 2 oxygens. Okay, so our formula is MO2. Okay, and this is one of the variable oxidation state we need to figure out because it's not part of the 16 in this hypothetical example. So to determine what the oxidation state of the M, we just set it up like a real simple algebraic equation because we know what the oxides are. So we got M plus, each oxide has a -2, right? Oxide always has a -2, and there's 2 of them. So we have a total of -4, and that equals 0, right? So we have M minus 4 equals 0. Solve for M becomes, it is a +4, it has to be. Okay, so M must be a +4 because the total of oxygens is a -4. And that's what I mean by calculating the charges on one or the other. And that's an example of the metal. Well, let's reverse it a little bit. What if it is calcium? And now we're going to do a hypothetical of Z2, okay? Z is a hypothetical element. And the question is, what is the charge of Z? Well, what do we know about calcium? Calcium always has a +2, all right? And there's 2 Z's, so we got 2 Z's equals 0. And so we got 2Z, we're going to move the +2 over, -2. Okay, so now we can divide through by 2. So Z becomes -1. Now, is it consistent with the formula? Yeah, because we know that calcium always has a +2. That means that in the way this is formed, Z being with 2 of them, each one must be a -1. Okay, because 2 of the -1s give me a -2, which is 0 when I add those up. And that's what I'm talking about here. You're going to know one or the other, depending. Now, right now, we're dealing with just neutral compounds, but we can do the same thing with respect to, say, polyatomic ions. Okay, so earlier I said it's a total number of cations plus the total number of anions normally would equal 0, okay? But I'm just going to add one more thing, equal the charge of the compound instead of 0. Because if it's 0, then obviously the charge of the compound is 0. But you can have a polyatomic ion that has a charge, okay? So for example, let's do NO3 negative. And the question is, what is, I'm going to change the color, what is the oxidation state of nitrogen here when it's bonded to 3 oxygens and there's a negative charge overall? Okay, so we set up this equation. We got N, which we don't know what it is. We're calculating it. Plus, we know that every oxygen has a -2, and there's 3 of them. So we got a total of -6 there. Okay, and that is equal to -1 because that is the charge of the molecule. So that's our formula here. We got N minus 6 equals -1. Solve for N, we got N is equal to 6 minus 1, and that is equal to 5, specifically +5. So under this condition, the nitrogen here has a +5 oxidation state. And each oxygen has a -2, that's -6, and the overall molecule has a -1. So this one, this equation, the bottom one, gives you a lot more latitude because there are some homework problems where they give you hypothetical compounds and they're asking you to solve what is the oxidation state of X or Y, okay? And you do the same, just calculate like I did here, okay? And you will be able to figure it out. In those homework problems, you could end up with a quarter fractional charge. And that's okay because it's just for an exercise. But normally we're talking about a whole number, okay? All right, any questions about that part? All right, so naming the ionic compounds, we got the name depends whether it's a fixed or variable charge, okay? And if it's a variable, we're going to use Roman numerals. I've done some of those examples already, okay? Now, in this case, the general formula for naming compounds is the metal name, that doesn't change. And then we take the non-metal, and then we add the IDE. Now, what is true about ionic compounds and covalent compounds? That the IDE remains the same whether we are working with ionic compounds or covalent compounds. Case in point, CO2, carbon dioxide, okay? Ionic compounds, magnesium oxide. Follow what I'm saying here? Let me give you an example. We have MgO or CO2. We got ionic compound here on the left and covalent compound. In this case, we have magnesium oxide. And over here, we have carbon. Carbon is a central atom. It remains the name carbon. And then dioxide. But it's still oxide, be it ionic or covalent. Okay? Thing to remember. The only difference The only difference between the naming of ionic and covalent compounds is the prefix. When you're dealing with ionic compounds, no prefix. Okay. Covalent compounds, yes, we do deal with prefixes, and more on that in a bit. Okay, so we have NaCl becomes name-wise sodium chloride, good old-fashioned table salt. All right, we have K, which is potassium, and then Br is not bromine, but is bromide because it's an ionic form here with potassium. So its name is potassium bromide, just like it was sodium chloride. Okay, this is bromide. I just did this one. Magnesium, name stays the same. Oxygen, ionic form of oxygen, its name becomes oxide. Okay, so magnesium oxide. Calcium, and then we have F2, which is not diatomic fluorine because the metal precedes first. You got the metal followed by the fluorides. And so it's not diatomic. It is two fluorides. So it is calcium fluoride. Notice it's not calcium difluoride, just calcium fluoride. Ionic compounds, no prefixes. You'll find in some ingredients, for whatever reason, they use prefixes of ionic compounds, which is incorrect. Okay, now there's an organization, a worldwide organization called IUPAC. It's initials for Union, International Union of Applied, I forget, chemistry and naming. Anyway, they're in charge of everybody getting together, representatives from all the countries, and deciding how to name a compound and the format. And the purpose of that is so that everybody is on the same page, because prior to that happening, we had all kinds of names going on. We had for copper, we used to call it cupric versus cuprous, and it's very ambiguous. And so to eliminate any ambiguity, everybody got standardized with respect to naming compounds. So that is so that a scientist from the other side of the world can interact with each other. And I personally had that happen to me when I was in graduate school. I had a scientist from Japan that came to study in our lab, and another one from Lebanon, and another graduate student, fellow graduate student from China. Now, our collective English, all of them, we conversed in English, but it was kind of challenging at times. However, we got on the board and we were writing chemical reactions, and we all understood each other of what we were attempting to do and attempting to create. Yeah, because the language of chemistry is fairly uniform throughout the world. All right, now we got lithium sulfite, not dilithium sulfite. The only dilithium you have is in Star Trek, okay? Dilithium crystals. No. If that really exists, I don't even know. So we got lithium sulfide, okay? And then we got Ag, which is silver, and then Cl, which comes from chlorine, which is now chloride. So we got silver chloride. Note, no Roman numerals here. Why? Because every metal here, potassium, magnesium, calcium, lithium, silver, are part of the 16, right? Fixed charges, okay? And the important part again is no prefixes. With respect to the polyatomic ions, I already mentioned this, that each polyatomic ion has their specific name. And so we got sodium nitrate, NO3, and that's its name. So we got this one here. We got potassium, 3 potassiums, and then we got PO4. Sometimes students tell me, well, how do I know that's phosphate? Well, kind of a good hint would be, we have the phosphorus, and then immediately following that, we got oxygen. So it's not phosphide, because if it was phosphide, it would be this, okay? no oxygen. But the moment you see oxygen following, you're dealing with a polyatomic ion. The same could be said for, let's say, calcium sulfide, okay? That is sulfide. But then if you got sulfide and then immediately following that, you got oxygen, that is sulfate, okay? So that's a good way to look at it, I think, and determine, am I dealing with ide or ate? To help you out. So we got potassium phosphate. And then in this scenario, you have parentheses. The fact you got parentheses, automatically go to the polyatomic ion table and look for the OH, what's in the parentheses, and that is hydroxide. So we got calcium hydroxide. Okay. Then, as is the case with PO4, here we got sulfur, you might think is sulfide, but we got oxygen following sulfur right away. So it's either going to be, depending on the number of oxygens, either sulfate or sulfite. If you look it up, you'll see it to be sulfate. So we got zinc sulfate. Okay, so, and again, you can mix and match here. You got potassium hydroxide, you got potassium sulfate, calcium phosphate, calcium sulfate, and the zinc. Again, you're building up your database with more different compounds. All right, with respect to the variable charge, as we hopefully know by now, you have to use the Roman numerals, okay? But you have to first figure out, like we just did earlier with copper chloride. Well, which copper do I have? Because I know copper is not part of the 16. So I got to use Roman numerals and I got to calculate which one. Well, I know that the chlorides each are -1. So I get a total -2. And so I got Cu minus 2 tells me that Cu must be a +2 state under this formula. So we're dealing with Roman numeral 2. Okay. And you end up with copper, Roman numeral 2 chloride. Now, no need to guess about it. You know, just remember that if you don't know what any of the, if they're not part of the 16, automatically you got to figure it out, which the anion, you should know what its charge is. You have to know that so you can calculate what the metal's charge is. Okay, here we got lead. We don't know what that is. It's not part of 16, so we have to deal with trying to figure it out. We know that the whole thing is equal to 0, and that each oxygen is equal to a -2, and there's 2 of them, and so we got a total -4 coming from the oxygen. So we got Pb minus 4 equals 0. Solve for Pb. Pb has to be a +4 oxidation state, okay? Which means we're going to be using Roman numeral 4 in parentheses. There it is, lead, Roman numeral 4, oxide, okay? Nickel, we don't know what that is, but we do know that each bromide is a -1, and there's 3 of them. So I got nickel minus 3 equals 0. Nickel has to be a +3, okay? So we're dealing with Roman numeral 3 for nickel. And then manganese, then sulfate. The sulfate is a -2 overall. It's a polyatomic ion. That means the Mn must be a +2. So that becomes manganese, Roman numeral 2, sulfate. And then here we've got copper. And we need to figure it out. We know that the NO3 nitrate is a -1. So we got Cu minus 1 equals 0. So Cu equals +1. Now I'm using the general algebraic formula. If you're comfortable without having to do that, by all means, I'm just laying out the steps for you until you become comfortable to figure it out. You could hopefully, at a glance, determine that that's a +1 charge. Okay. Just because you know that the NO3 is a -1. Okay, name-wise, that would be copper 1 nitrate. Okay, which also could be the other formula. Think about this. You also have this format. Okay, and we know, like we just said, each one is a -1. So there's 2 of them that tells you that this must be copper 2 nitrate. Okay. Copper 2 nitrate. Now, iron, there's 2 forms of iron. There's a +2 iron and a +3 iron. So this is Roman numeral 2 up here, and Roman numeral 3 for iron. And I can all mix and match here. Again, I can do the lead bromide, lead sulfate, lead nitrate, nickel sulfate, etc. So again, we're building up your database. Oh. Yeah, cobalt and nitrite. I almost said nickel, and nickel in the brain. Okay, so nitrite, we know that the nitrite is a -3. Okay, that's a -3. So that implies that cobalt has to be a +3. Okay, because we put them together to equal 0 overall. All right, so what we have here is cobalt, Roman number 3, nitrite. Cobalt's has some nice blue colors, very pretty colors, some of these metals. In fact, fireworks, when you see all those bright colors, you're looking at a lot of metals up there getting excited and exhibiting their colors. All right, this is a little more challenging. Let's break it down. Okay, you can, at a glance, look at that formula and very quickly say, you know what? This is iron 3. Okay, well, let me explain. We got this formula, CO3, -3. All right, what we don't know is the charge of the iron, but what we do know is this. We have a -2 for every other carbonate, the CO3. And there's 3 of them. So we got a total of -6. And there are 2 irons. So 2 irons, and each cobalt has a -2, and there's 3 of those. So that's a 2 times -2 is -6. So our formula is 2F - 6 = 0. And so I can rearrange that sulfur Fe. It gives me +6, and then divide through by 2. And guess what? Iron in this state is a +3 oxidation number. Isn't that what I just told you before we did all the calculation? Why? Because remember, I said earlier that the subscript of the anion is the charge of the cation, and vice versa. And so here's the subscript of the anion. That will be the charge of the cation. And the subscript of the cation will be the charge of the anion, which is a -2 for the carbonates. Okay, so at a glance, you can, boom, there it goes. But if you're not sure, break it down like I just did with the charges and then solve for the one that is not known. So we're dealing with iron, Roman numeral 3, carbonate. Okay. Okay, so we have here we're asked to either give the formula or give the name. Okay. All right, so here, obviously, we're being asked to give the formula. We are combining the hydroxide with SR strontium. Well, we need to know what the charge is for that. We need to find it. And you will see that it's a group 2A element, which means that strontium has like magnesium and calcium will have a +2 charge. It has 2 valence electrons. So we have SR +2. And then we have the hydroxide. Each one's a negative, so we need 2 of them. So we're going to need the parentheses. So we got SR parentheses OH subscript 2, strontium hydroxide. All right, number 2, it says just name AU. AU is gold. Gold is not part of the 16. So therefore, we need to calculate what is oxidation state. So what we do know is gold, and we know it's going to be some parentheses, and then the C ions are chlorides. So this is what I know. So I write down what I do know about that formula. Now I've got to calculate what gold is, okay? Because each chloride is a -1. There's a -3 total for the chlorides. What does that infer? That the gold must be a +3, okay? In order for that formula to be equal 0. Okay, zinc +2, oxide -2. So straightforward, ZnO. All right, barium and phosphate. And so barium has a +2, and the phosphate has a -3. Okay, so we have a dissimilar charges here. What do we look for? We look for a common number. Again, in this scenario, common number 6. So we need 3 bariums and 2 phosphates. Okay, so we can go Ba3 parentheses PO4 subscript 2, barium phosphate. And then over here we got lithium, which is a +1. And then we got SO3. Be careful, SO3 is not sulfate, it is sulfite. Okay, so we'll put it together. We need 2 lithiums for every sulfite. So that's our formula. And then here we got a aluminum is a +3, and sulfur becomes sulfide. All right, so here we're going to put them together. And the same scenario like we did with the barium, we find common ground here, which a common number is 6. So that means I need 2 aluminums and 3 sulfides. So our formula will be aluminum subscript 2, sulfide subscript 3. Okay. And then finally, we got copper, and NO3 is nitrate, and there's 2 of them. We know that each one is a -1, so that gives us a total -2, which means that copper must be a +2. Therefore, Roman numeral 2. Okay. So let me clear my mess and bring in something that's not as messy. Okay, so strontium hydroxide for the first one, gold 3 chloride for the second one, zinc oxide for the third one, barium phosphate. Okay, there were dissimilar charges, so I found a common ground, which was 6. I need 3 bariums and 2 phosphates. Lithium sulfite. Okay. The biggest error is not recognizing that there's 3 oxygens versus 4. So read the formula carefully. And then we have aluminum and sulfur becomes aluminum sulfide. The similar value here, because we got aluminum has a +3 and the sulfide has a -2. Okay, so we end up with 2 aluminums, ions, and 3 sulfides. And then the last one, copper to nitrate. All right, now, again, you can mix and match, okay? Put the strontium with the chlorides, the oxide, the phosphate, the sulfate, even the sulfide, and of course the nitrate, and do the same for the others, okay? So you're building, getting more, your database is getting bigger and bigger with respect to naming compounds and writing formulas. All right, any questions about this at this point? Okay. Let's do one more real quick, these, and then we're going to get into the covalent compounds. All right. You're asked to write the formula. So step number one, write the ions first. Sodium will be a +1. And the nitrites, you got to be careful, nitrites, not nitride, big difference. Okay. Look at the polyatomic table and you see that's the formula. And together it's a 1-to-1. Okay, here we got nickel 3, tells you we got using +3, and then the oxide, -2. And then we got magnesium +2, and the iodide -1. So I'm writing all of these in ionic form before I put them together. We got aluminum, which is always a +3, and the cyanide, which is a polyatomic ion, which is Cn-. Okay. So everything's written in ionic form. Now I can put them together with the right numbers of each. So here's a 1-to-1. So it's just sodium nitrite. Here we got a dissimilar charge, so I need 2 nickels and 3 oxides. So I got Ni2O3. Magnesium, we just need 1 magnesium and 2 iodides. And then we need three cyanides for aluminum cyanide, so it becomes Al(CN3). Okay. And that's what I got. And here, again, write them into ionic form first, and then figure out how many of each you need to put together so that their overall charge equals 0. All right, that is for ionic compounds, which is a combination of metal and a non-metal. Okay, now let's talk about molecular compounds, or covalent. Okay, that's simply a combination of non-metals used here. Now here, we don't deal with charges, okay? We're not dealing with charges, we're dealing with partial charges. Remember the polar bond? And so what's happening here is the following. I've been using extensively the term charge, for sodium has a charge of +1. Well, I can't really do that with respect to ionic molecular compounds or covalent compounds, because they have a partial charge. So what we do is we collectively, be it ionic compound, be it covalent compound, we use the term oxidation number, okay? So the oxidation number is still a negative or a positive, and most of the time it depends. It could be a -1 or a +1, but it also takes into account whether we got a full negative charge or a partial negative charge. And so we just use the term oxidation number, and I'm going to try to revert that. It's hard to go to just use oxidation number, because up to this point I've been calling it charge. So I'll go from there, calling them oxidation number. All right. The other main difference about covalent compounds versus ionic compounds. If I take an ionic compound and I place it in water, depending on the solubility, what's going to happen is this. let's say I got an ionic compound. Remember, the bond that they make, ionic bond, is like two magnets, okay? There's no sharing of those electrons. They're like two magnets attracting to each other. Well, when I put them in water, what happens is they totally dissociate, they break apart. They form ions, okay? Some of those ionic compounds dissociate 100% and make very strong ions. I shouldn't say strong, it makes it into a very conductive solution. Some ions, they don't break apart 100%. They may break apart 5%, maybe less. So yes, there's still some ions, but as far as a lot of them, there's not a lot of them. And what I mean by conductive is this: if you take pure water and I put in electrical cables in there, it will not conduct electricity, okay? Because there's no ions to close the circuit. The ions act like the light switch. You flip the switch on, you close the circuit, you get electrons traveling from point A to point B to light up whatever you're going to light up. If there are no ions, there's no current flow, okay? The moment you put ions in there, you get current flow. And so in pure 100% water, you really can't get electrocuted if you put anything in there electronic. I wouldn't do this at home, okay? But as soon as let's say you stuck your hand in there, after a few minutes, the material off of your hand, because we got salts and all kinds of conductive ions in our hands, will get into solution. Now you better get out of the water because it will conduct electricity and you get electrocuted, okay? Covalent compounds do not break apart. Why? Because they are sharing a bond, equal sharing or non-equal sharing. There's only one example of a covalent compound that literally breaks apart, and that deals with the next chapter, which deals with the acids, okay? But for right now, we're just saying that covalent compounds, when I place in water, remain intact. They don't form ions, they're non-conductive. If I take pure 100% sugar and 100% water, and I put it in a water solution, okay, I just make sweet water. If I try to put a current through it, there's going to be no current because the sugar is not breaking apart to form ions. So it is a non-conductor, okay, non-conductor. And that's one of the main differences between molecular compounds and ionic compounds, is the ability to totally dissociate or partially dissociate with respect to ionic compounds, right? Now, with respect to naming covalent compounds, we do use prefixes. I mentioned this before, okay? Don't mix and match. Ionic compounds, no prefixes. Covalent compounds, yes, prefixes. And the prefixes we normally use is mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, and octa for 8. Occasionally you see nana for 9 and deca for 10. Okay, so those are the prefixes we generally use. Now, you will have in covalent compounds a central compound, okay? And if it's a central compound, 99% of the time it is written first. And let's say the central compound is bromine. Well, it's not, when it's a central compound, the name remains as bromine. If it's not the central compound, then bromine becomes bromide. Note the difference, okay? If it's a central atom, the name stays the same. If it's not, if it's attached to it, we remove the INE and put the IDE. We'll have some examples of that in a minute. So we have the first non-metal central atom, its name. It may have a prefix or not. Depends how many you have. And then you have the non-central elements, which again may have a prefix. And then we do change the name to IDE. So oxygen remains as oxide. Sulfur now goes to sulfide if that's not the central atom. Okay. If the first central atom is by itself, we just call it whatever it is by itself. We don't use mono. But if the second nonmetal is by itself, we use mono as a prefix. Case in point is as follows. CO versus CO2. Okay, we know this is carbon dioxide. 2 oxides. Okay, whereas the top one is carbon, guess what? Monoxide. Monoxide. Notice the naming, the prefix. When you want to combine mono, if you put together two, it sounds like I'm being given an English class. Okay, let's say I want to put mono and oxide together. Okay, well, I got 2 vowels coming together. I have to drop one of the vowels. And so that's why when I put them together, it becomes monoxide. Okay. Tetra, let's say it was the oxide. Well, by the rules of English, I'm supposed to drop the A. And so it becomes tetroxide. Well, all right. If you forget to drop the A or not, I'm not going to be too concerned about it in the naming of it. But I have to introduce it. Some instructors are stickers about it. All right, we got this one here. Central atom is carbon, okay? Written first, and then whatever follows is the nonmetal attached to the central atom, which in this case is oxygen, which becomes oxide. So as I stated, the name of this one is carbon dioxide. Now, here's carbon monoxide. Okay, notice the trend. Now, here, what we do is, my suggestion is as follows. Write down the base name. Okay, we got phosphorus. Now, phosphide, because the phosphorus, these 2 phosphorus are the central atoms. So we don't change its name, it still remains as phosphorus. And then we have oxide. Okay, so that's the base name. Now go back to see how many of each you have. Well, we got 2 phosphorus, so that becomes diphosphorus. And we got 5 oxides, so it becomes pentoxide. Okay, so parent name first, followed by the prefixes. That'll help you out. Systematic approach to naming these things. And if you start with the name here, you work backwards. You put down the formula for the parent name, which is phosphorus and oxide, and then you put the prefix, which is 5 and 2. And we're going the other direction. So diphosphorus pentoxide. This is what I mean that A wasn't dropped there. All right, anybody want to give this one a shot?
It's phosphorus trifluoride.
You got it, exactly. So the parent name is phosphorus, like the first one. The F is fluoride, so that's the base name, and then go back and put the prefixes. Phosphorus by itself, you don't need to add the mono, you just say phosphorus, and then there's 3 fluorides, so it becomes trifluoride. Okay, notice that the I wasn't dropped because the F is not a vowel. Okay, so it's trifluoride. All right, so how about this one? Okay, iodine is the central atom, and then we got 7 fluorides around it. So we write down the parent name, iodine, okay, and then the fluorides are attached to the central atom, so they become fluoride. There's only 1 iodine, and then there are 7 fluorides, so it's hepta fluoride. Iodine, heptafluoride. Okay, so here, given the formula, write the name and vice versa. Okay, so now we're given the formula, you're asked to write the name and just reverse the process. Okay, so we have the central atoms here, always written first. And so we got bromine. And then followed by the oxides. Okay, we have 3 bromine, so it's tribromine, and 8 oxide, 8 oxygens. Okay. Okay, how about this one? Somebody want to try that one?
That's Tetra, Phosphorus, Hepta, Sulfide.
You got it. So parent name, phosphorus and sulfide, and then write the prefixes, you end up with the sulfide. Okay. And then we got, this one's pretty straightforward. We got sulfur and 3 oxygens, sulfur trioxide. Very smelly material. If you're ever behind a vehicle and you smell like a rotten egg smell, you're probably smelling some of this, and plus a bunch of other chemicals. This guy goes up in the atmosphere and then forms sulfuric acid eventually, which is an acid, and then somewhere down the road it rains, and then you have what's called acid rain, which causes all kinds of problems. All right, so now we're given the name and we want the formula, so we're working backwards, and we do the same thing, just reverse it. Okay, and so I have iodine, there's only one, so I can just do simply I, and then I have fluoride, which is now where we had the base name, now I got the base formula. Okay. Once I got the base formula, I come back and do the prefixes, and then there's 6 of them, and that's a done deal. So IF3, 6, excuse me. Okay. And then dichlorine pentoxide. So same thing, reverse it. We write the parent name, which is Cl, and then oxygen, and then go back and substitute in the prefixes, which is 5 and 2, Cl2O6, O5, excuse me. Okay. And then now here we got diphosphorus tetraiodide. Okay, and even in this state, you can still calculate what the oxidation number is of one or the other. For example, if we were to take, let's take the last one we just did. All right, we know that the overall charge on this P2O4 is 0, or oxidation state of the whole molecule is 0. We know that each iodide, because we're dealing with iodide, is still -1 in this state, and there's 4 of them. So I got -4. And there are 2 phosphorus. So I don't know what the oxidation state is on each phosphorus. So there's 2 of them, so I got 2p minus 4 equals 0. So I got 2p is equal to a plus 4. Divide through by 2, and phosphorus in this scenario is a +2 oxidation state. In each one, there's 2 of them, so each one has a +2 oxidation state. And I can do the same thing for all the other ones if I need to calculate the oxidation state of the central atom. Okay. Here, iodine, right here, has a +6 oxidation state when it's bonded with 6 fluorides. Okay. So a couple of reminders. Prefixes are only with covalent compounds, okay? And excuse me, Roman numerals are only used for those metals that have a variable charge and variable oxidation number, like copper, iron, cobalt, lead, all of them. All the other metals are variable. And you don't know what they are, but you always know what the partners are, whatever they have bonded to, and you can calculate what oxidation number they are working with. Okay. The polyatomic ions in the table, we don't change the name because I've seen a lot of times the NO3 and the nitrate has been name changed like nitrogen trioxide, which is totally 100% incorrect. It's just nitrate. Okay. And you might try these at home, see what you get, write the formula or the name, and you should end up with this. So BaCl2, NO2, Fe3, parentheses PO4, subscript 2, diiodine tetroxide, silver sulfate, nickel 3 sulfide. So try those at home, without I gave you the answers there, but try them at home and see if you can work them through and go back and forth with the name, go to the formula, vice versa. All right, now there's the worksheet. Don't forget to do those. They help you out with the nomenclature. Other than that, congratulations, you are done with chapter 8. And we will begin chapter 9 here in a second. So let's take like a quick 10-minute break here. So I got 132, call it 140, call it 145, 15 till. Okay, and then we'll continue with chapter 9. Or if any questions you have, we will start with that. All right, we'll be back till 1:45. Okay, I'm back. What I want to do is, as I stated earlier, when it comes to this nomenclature, I don't want to leave it quite yet. I want to talk about a few more things here. But there is in the module that deals with this chapter, there are some additional resources in there to help you out to name for nomenclature, specifically what are called polyoxy acids. And I'm going to talk about that here in a second. In that, where is it? In that module, for your resource, there is a file, PDF file, that deals with common polyatomic ions, which is a list a little bit more than what we give you, but there's for your information there. Okay. Also, there is a nomenclature of what is called nomenclature of acids. In the next chapter, we're going to talk a lot about acids. There are what we call binary acids, which deals with a hydrogen bonded to a non-metal, like HCl, hydrochloric acid, for example. And then there are number 2, oxy acids, which consist of hydrogen bonded to oxygen and a third element, okay? Then we deal with some organic acids, which we're not going to talk about a lot, or in fact, we won't even mention it. Organic acids. I may say a word or two of some organic acids you're already familiar with, for example, vinegar. Vinegars and organic acid. Anyway, the naming, for example, for hydrochloric acid, which is in your stomach, it comes from the chloride ion, which is Cl minus, and we just simply put a hydrogen with it to tie up the negative charge, and you have hydrochloric acid, okay? If it's in a water solution. Now, in the nomenclature exam, there is a distinction between an aqueous, HCl, and a non-aqueous. So if it's aqueous, meaning it's in water, it's called hydrochloric acid. Okay, if it's not, it's just simply hydrogen chloride. Okay, then we talked at length about the NO3 polyatomic ion, and a lot of these polyatomic ions come from acids. So if we put the hydrogen back on, we end up with HNO3. Okay, hydrogen, normally you can tell that is an acid because hydrogen is written first, and nitrogen here is the middle species. But HNO3 is also known as nitric acid once the nitrate ion the hydrogen is put back on. Now, the way it's removed is treated with the base. Classic example, you got hydrochloric acid in your stomach, you have, maybe too much Taco Bell, your stomach's not doing too good, and maybe a little acid reflux. What do you take? Tums, which is a base, Maalox, which is a base, and that neutralizes some of the acid. And then when you neutralize it, you form the salt, nitrate. And then you have things like nitrite, which is the nitrate ion minus one oxygen. We'll have more on that here in a second. Once you put the hydrogen back on, it's called nitrous acid. And then we're going to see here, there's a whole slew of oxy acids, which contain the chlorine, okay, the perchlorate. And it sounds confusing here in a bit, but once we go over how we create these ions, and then when you put the hydrogen back on to make it an acid, then this part here tells you the name. So the perchlorate ion becomes perchloric acid, or chloric acid, or chlorous acid, or hypochlorous acid, et cetera, et cetera. So there's a lot of good information to help you out with respect to naming these acids. So let's talk briefly about the nomenclature of these polyatomic oxy ions and how they came about. The file lists another YouTube video, which another scientist talks about this, and I borrowed a little bit, and I'm going to have my little version of it. So normally when we deal with the polyatomic oxy ions, we're only dealing with the upper right part of the periodic table. If you look at the periodic table and you got the boron, the carbon, and nitrogen, notice that they are listed, or they're in blue, okay? And then below carbon, we got the ones listed in yellow. Okay, there's a total of 9 of them, okay? And then we go across to group 7, we have chlorine, bromine, and iodine. Okay, so those are the elements in themselves. Now, the blue color going across, if you put on top of the boron a -3, that's going to help you here in a bit. In front of carbon, top of carbon, a -2, and then nitrogen, a -1. Okay, that's for the blue. Now, for the yellow, that first column, which would be group 4, silicon, the beryllium, and stannous, which is 10, that is -4. So everybody in the first column under SI has a -4. The next group over in yellow has a -3 and -2 for the following group, okay? Those are going to represent, those numbers, those negative values are going to represent the overall charge of that polyatomic ion, okay? And then finally, the last group has a -1. Now, the base name is the ATE, okay? The 8. And so for the ones in blue, all the ones in blue, their base name, there's only 3 oxygens. So we got boron with 3 oxygens, it has a -3. Notice why that -3 was on top of that. The carbonate, like sodium carbonate, has also 3 oxygens, and it has a -2 overall charge for that polyatomic ion. And the nitrate, which you're familiar with now because we've been talking about it at length, has 3 oxygens and overall has a -1. So that's what that -1 was all about on top of this, -2, -3, okay? Now, if we look at all of the ones in yellow, the base name, because to name these things, we start with a base name. So everybody here will have the ATE ending. So everybody in yellow will have 4 oxygens bonded. So we got 4 oxygens bonded to silicon and so forth. Oh, and phosphorus, and you look at that, and you recognize the PO4, phosphate, right here. Change the color a little bit. The PO4, the phosphate, and the sulfate. Okay. Now, and then finally, the last group in green all have, like the ones in blue, just 3 oxygens. So you got the chlorine bonded to 3 oxygens, the bromine to 3, and the iodine to 3 oxygens. All of them have a -1 charge. Okay. Now, all the name for each and one of them, which we're going to show you here in a second, the base name has the ATE extension. So we got borate, nitrate, carbonate, etc. Okay. All right. So this is kind of helps you out with respect to how many oxygens these guys have. Okay. So, and then we're going to do now, we're either going to add an oxygen to this group, or we're going to remove an oxygen till we're back to the element itself. Now, some of these compounds do exist, some do not. Some are hypothetical at this point, haven't found them yet. So, but they're predicted to be there, so maybe they will. But they're probably very unstable. So that is the parent formula for this group. The ones in blue, the ones in yellow, the ones in green. Now, let's take the carbonate example, and you can apply it. Down here at the bottom is the base name, the orthosilicate, germate, stannate, phosphate, arsenate, antimonate, sulfate, selenate, terylate, chlorate, bromate, and iodate. Okay, that is the base name of those polyatomic ions. Right there. The ones in blue, yellow, and green. Okay. Now, if we take just the carbonate all by itself, or if we got the boronate, carbonate, and the nitrate. If we take the carbonate, which is right here, and if we remove 2 oxygens, we end up with CO-2. We have to change its name now. It's no longer carbonate because we removed 2 oxygens. Now it becomes hypocarbonite. Okay. If we remove 1 oxygen, it goes from carbonate to carbonite. You know, like sulfite, sulfate to sulfite, goes from 4 oxygens to 3. The base formula is number 3, and we can add an oxygen to it, and we have to put the prefix PER, per carbonate. So the 3 names for the 3 species, depending, going from the base name, carbonate. If we add an oxygen, it becomes percarbonate. If we subtract 1 oxygen, is carbonite. Subtract 2 oxygens, becomes hypercarbonite. And if we get rid of the last oxygen, we end up with C-2, that's carbide. Okay, and you can do the same thing with all the other ones listed right here. Okay, you start off with the base name, and then you're going to remove oxygens until you go from sulfate, okay, to all the way to sulfide. Okay, so that's a little tool to help you out with these polyoxy acids. Normally, we tend to use a lot. You might see, with respect to the nomenclature exam, you'll see a lot of use of that, and obviously the sulfate, the phosphate. That's about it, really. Okay. All right. So all this is there on the nomenclature module. And it's available to you to help you, a study guide to help you with the nomenclature exam. Okay. All right. So, any questions? Well, let us continue now. And we introduce this chapter 9, which deals with acids and bases. And as I mentioned, you're familiar with an acid because it's roaming around in your stomach right now. And that is HCl, hydrochloric acid, being in an aqueous solution. Okay. Now, let me explain what this H plus is all about. We call that H plus. It's hydrogen, obviously, with a plus charge. It's the ion. We call that a proton. Okay. Now, let's think about hydrogen. Now, we go back and remember how we did the Lewis dot structures for the atoms. Hydrogen would have one dot. It's the first element. It's only got one proton and one electron. Okay, its electron configuration would be 1s1. Okay, now recall that the s electron can handle, and this is the hydrogen atom. Okay, recall that this is hydrogen. The s has room for one more electron, and sure enough, hydrogen can actually pick up one more electron to fill that electron configuration. Okay, the result is that because it has an extra electron, what do you think? Just like the nonmetals on the far right of the periodic table, it has a negative charge. We call that guy, it has his own little special name, hydride. Sound familiar? Chloride, iodide. In fact, in some periodic tables, hydrogen is placed not only in group 1, but it's also placed underneath group 7, because it can pick up one more electron and fulfill its duet rule. That's called hydride. Now, the reason they put it in group 1 is with the other metals is those metals lose one electron to end up with a plus charge, right? So it loses that one electron, and that 1s1 is empty now because its orbitals, there's no electron there, it's empty. And that is what we call the proton. That is what is defined as any species, it has a specific name, but any chemical that produces a proton when placed in a solution of water is an acid, okay? And hydrogen, like I said, is very unique because it has that capability of gaining an electron or losing that electron. By itself, it's not very stable, and that's why it's diatomic. It needs to hook up with another one to stay stable. But the protons are stable and they exist in all around us, okay? They're ions. All right, let me clear this up. Some of the properties of protons, they are sour taste. Lemons, very acidic, okay? Pickles, very acidic. In pickles, you probably have acetic acid, which is vinegar, tastes very sour. They can be very corrosive. Acids are corrosive. The stronger they are, they can really destroy and dissolve metals, okay? Now, we have in the lab what's called litmus paper. You may be familiar with this, but there's 2 types of litmus paper. This is blue litmus paper, and there's also red. And what this does is just simply tell you if you place this solution, which you don't know what it is, and you put it in the blue litmus paper and it changes its color to red, what that indicates is that that solution is acidic. It doesn't tell you anything about what kind of an acid or how strong of an acid. It just tells you it's acidic because it changes blue litmus paper to red. Okay. All right, now with respect to bases, what comes in hand here is anything that produces, we call this polyatomic ion, the OH, we call that the hydroxide ion. There's a lot of examples at home. You may have some liquid plumber, for example. Liquid plumber is you put it in your drain, clogs it up, unclogs the drain. Most of that is a base, very strong base. In fact, if you get some on your finger, it may feel slimy. You may think it's the chemical, but what's happening is that sodium hydroxide will start to dissolve the tissue of your skin and make it into a gelatin-like, so your skin feels like it's slimy. Make sure you wash your hands properly. It will dissolve some skin. There's a lot of makeup products out there that contain an alkali material. I guess the idea is to remove a layer of tissue and rejuvenate the skin or something. I think that's what it does. Now, if you were to taste it, which I wouldn't recommend, it's bitter and in solid form, it's kind of chalky looking most bases. Okay. Feels soapy and slimy again, simply because you're just denaturing your tissue. Now, it will take red litmus paper, and if you have an alkaline we call base solution, and it turns it blue, again, it tells you that it is a base. That's it. Okay, that's all I can tell you. Now, there's two definitions of acids and base. The original definition was by a scientist by the name of Argenius, okay? So Argenius, the definition of a Argenius acid is that any chemical, when placed in an aqueous solution, which means a water solution, when it's dissolved in a water solution and it produces a proton, okay? Remember, the ionic compounds I explained earlier that when I put them in water, you put them in water, they break apart. Okay, I take sodium chloride, table salt, dissolve it in water. It's very soluble. It breaks up totally into the sodium ion and the chloride ion. Okay, and I said the covalent compounds don't do that with one exception, and that is here, this acid. This acid, this is a covalent compound. You got two nonmetals, hydrogen and chloride, two nonmetals combining. But the nature of the beast is that acids, when dissolved in water, tend to break apart. Now, some acids break apart completely, and those are very strong acids. But there are other acids that break apart a little bit, not a lot. And those are what we call weak acids. Hydrochloric acid in your stomach is a strong acid. Vinegar, aka Italian dressing, okay, that is a weak acid, okay? Weak acid, but nevertheless, it will dissolve partially in water to produce protons. So, Argenius definition, acids produce protons in aqueous solutions. A Argenius base is any chemical that, when dissolved in aqueous solution, will produce the hydroxide ion. That generally starts with ionic compounds. Most bases are ionic compounds and metal-nonmetal combination, okay? Now, the cool thing about this is the following. When, and this is an introduction to your first type of chemical reaction, okay? When a proton reacts with a hydroxide ion, you produce dihydrogen monoxide, aka water. Okay, so that's a neutralization reaction. And so back to the Tums in your acid, you take Tums, which is the base, it reacts with the acid in your stomach and neutralizes it. Okay, neutralizes the acid in your stomach, producing water. So something to think about. Okay, because I know some people like to drink alkaline water. Now, I want you to think about it and make your own decision. Alkaline water is a base. you ingest it into your stomach, which is an acid, a very strong acid, and that alkaline water gets neutralized. So the alkaline component, which is a base, is destroyed and now makes up water and the salts of whatever the other components are. So benefits, I don't know, because it's you destroy it pretty quick, okay, once you drink it. Anyway, food for thought. All right, so acid and base, and this is your first type of chemical reaction, a neutralization reaction. We get an acid and a hydroxide. You might ask, well, how's that happen? Well, let's think about this for a second. If we look at the Lewis dot structure of the hydroxide ion, okay, you will find 3 pairs of electrons on the oxygen. It has a negative charge. Recall the proton has a positive charge. And remember, it started off with a 1s1 orbit. Well, that orbit is empty. And so now with that empty orbit, it can take a pair of the electrons from the hydroxide and just insert there and form a bond. So now it forms a bond as follows. Okay, and you form water. Okay, it has that capability. That's the cool thing about it. Okay, so the rehash, the Argenius acid produces, by definition, a proton in solution, and the Argenius base produces the hydroxide ion. This definition worked pretty well, except there are other examples of an acid and a base that had nothing to do at all with the hydroxide ion, but it's still a base or an acid. And excuse me, this is a chemical reaction of a neutralization reaction, your first reaction, the first of the 6 that we're going to eventually talk about. So you have an acid, in this case hydrochloric acid. Here is the proton that's going to produce. Here is the hydroxide it's going to produce. Those two get together and generate water. Okay. And then what's left is the sodium and the chloride, and it just forms a salt. Now we tend to use the term salt in our everyday terms as thinking of it being sodium chloride. Well, that's, yes, that's correct, but you have a large number of totally different salts. It doesn't have to be sodium chloride. It's basically an ionic compound, which can be any metal and any non-metal, okay? You're not limited simply to the stuff you put on your French fries. All right, so that's an example of a neutralization reaction. Now, acid plus base produce a salt and water. So as I mentioned earlier, previously here, that I said that that Argenius definition worked fairly well to be able to define what's an acid, what's a base. But there were examples out there that had nothing to do with hydroxide whatsoever, but yet they were neutralizing the acid, okay? And what that is another definition had to be formed, and it's where Brownson and Lowry came into play. And they expanded the definition. In fact, their definition encompasses a lot more bases than the definition that was limited only to the hydroxide. Now, they're very similar with respect to how to define an acid, because the Argenius acid creates a proton, and the Brownson-Lowry acid is any chemical that loses a proton. Well, aren't you doing the same thing? You're producing a proton. There's a proton being involved in both cases. Either you produce it, you lose it, either way it's there. Where they differ is how they define a base. So the Brownson-Lowry base is defined as a chemical that will accept that proton, okay? Recall that I explained earlier, I said the hydroxide ion had those lone pair of electrons. And here comes a proton that had that empty orbital, and they ended up, inserting the lone pair on the hydroxide can then create a bond with the proton. Okay. Now, when we did the Lewis dot structure for ammonia, this is the formula. Guess what? It had a lone pair sitting there in the central atom. We have a proton that's being generated, just like up here, but its lone pair S1s orbital is empty, and so we have the same interaction here that we have with the hydroxide and the proton, tying up that proton that was generated by the acid and formed this polyatomic ion, which we're familiar with because it's listed on our table, the NH4 plus. Okay, and that was called the ammonium ion. So either way, what's happened is the Brownsville-Lowry base tied up that proton and neutralized that proton to create a salt. Okay, and down here is a three-dimensional model to kind of show you. Right here could be the lone pair sitting in there. So that proton then attaches itself to that lone pair to form the polyatomic ion there. Okay. Okay, so ammonia here is a Brownsville-Lowry base. It's not an Argenius base because it's not producing any hydroxide ions, but it is a Brownsville-Lowry base. So you can see here how this definition really, there's a number of a bunch of other compounds out there that can act as a base because their ability to have lone pairs on them and tie up this protons. All right, so we're going to talk about what are called strong acids and strong bases. And what we mean here is back to the dissociation process, okay? That's the main difference here. It's a matter of just dissociation and the degree of dissociation, the degree of dissolving in aqueous solution. If only a little bit of material is dissolved in solution, then it's a weak acid or base. But if that material dissolves roughly 100%, it is a strong acid or strong base, okay? Because there's more material. And the other way to look at it is, as I said, the more ions go into solution, and the more ions you go in solution, the more electricity that it conducts. And so if literally all the material breaks up and you create 100% ions, you're going to get a strong current running through that if you're running electrodes through your solution. But if only a small amount of ions are formed, yes, it will conduct electricity, but it will be not a strong current, okay? So strong and weak is a function of how much of material goes into solution. Some examples of strong acids, okay? HCl, which I told you is in your stomach, hydrochloric acid, is a strong acid. Literally approximately 100% of it, and we say approximately, nothing's ever 100%. 99.99% of it goes and breaks up completely, dissociates, and breaks up into the ions. So HCl is one example. HNO3, which comes from the nitrate ion, we put the hydrogen back in, and now it's called nitric acid, okay? And then check this one out. SO4, that's the polyatomic ion sulfate with a -2 charge. We put 2 protons back in there, we have now sulfuric acid, okay? Sulfuric acid. So these 3 chemicals are strong acids, very strong acids. Literally dissociate roughly 100%. Some examples of strong bases are KOH, which is potassium hydroxide, and NaOH, which is sodium hydroxide. We're going to learn, we haven't introduced this yet, but we're going to learn that the reason these guys are strong is because they exhibit a lot of solubility in water. We have some solubility rules for chemicals. We're going to be able to look at ionic compounds and determine how soluble they are. We're going to be either defined as soluble or insoluble. And even though it's insoluble, always remember that a little bit goes in solution. The solubility rules tell us that potassium hydroxide and sodium hydroxide are very soluble in water. Therefore, they will totally dissolve in solution and very strong, okay? And there's the an example. Sodium and sodium hydroxide breaking in solution. Now, how do we demonstrate a strong acid and a strong base in diagrams? Okay, well, we do that as follows. The one on the left is hydrochloric acid. That depicts a strong acid because literally all of the ions, you can maybe use 3 or 4 pair of the ions and show them. Here we got 3 pair, 3 chlorides, 3 protons. They're all separated. That depicts a strong acid. The one on the right, we got 3 hydroxides, 3 sodiums. That depicts a strong base, okay? If it wasn't a strong base, then what will happen is they will stay together in solution, right? So when you write your diagrams, don't forget to write the charges on them because that is what's happening, okay? You are forming ions. Don't forget to write the ions and don't forget to write enough that are paired to each other. So you wouldn't put just 3 chlorides by themselves because you got to have the corresponding counter charge, which is 3 positives. And the same here. Here they show 3 hydroxides and 3 sodium ions. Don't forget the charges that depicts them to be in solution. This kind of represents a beaker full of water, okay? All right, so here's the examples of strong acids is hydrochloric acid, nitric acid, and sulfuric acid. Strong bases, sodium hydroxide, potassium hydroxide. In fact, any hydroxide that exhibits that is defined as soluble by the solubility rules, which we're going to learn, is a strong acid base, excuse me. So what does it mean again? That is that basically that literally all the compound dissociates 100%. Okay. Now, weak acids. Weak acids are those examples of chemicals that do not dissolve 100%. They may just dissolve maybe 1 to 5%, small amount. And what we do is we depict a double arrow, okay? Notice that the ones before had a one-sided arrow right here, one side, one direction, to left to right. Whereas these here to show a double arrow. Okay, bear with me for 1 second. Give me 1 second. All right, so I'm back. So we show this as a double arrow going right and left here. I circled it. Okay, what this means is this, that the rate of going from left to right equals the rate going from right to left. And that here, this is general formula of a weak acid. This happens to be what we call acetic acid, aka vinegar. When it's in solution, it's an example of what we also call an organic acid, because there's carbon and hydrogen involved there. It will produce a small amount of proton and the corresponding salt, okay? So, but the bulk of this would be, you know, maybe this is like, you know, 95% of it is still in this form. And maybe a little bit in the form of ions. If we were to measure the conductivity of a solution, and that is how much electricity can run through the solution, it would be very weak, okay? It would be weak because the number of ions is much less compared to a strong acid that has a bunch of ions because it's more soluble. All right, so some examples of weak acids. And guess if you've seen the train here, let me back up for a moment. Okay, you know, the hydrochloric acid came from the chloride ion. The nitric acid came from the nitrate ion with a negative charge. And the sulfuric acid came from the SO4 sulfate ion, the -2. If we put the hydrogens back up, this is sulfate, nitrate, and the chloride ion. And putting hydrogen back up there, remember that hydrogen proton with that lone pair, its orbital missing, the extra electrons are on the oxygens and they can hook up again to form the acids, okay? All right, so if we look at the next group, guess what? We have a similar thing, carbonate, CO3 -2. Acetate, if you look at the periodic, polyatomic ion table, you'll see the acetate ion. And look at this one, phosphate with 3. Okay. And then the fluoride, this is hydrofluoric acid. And so these guys are all weak acid, carbonic acid, acetic acid, phosphoric acid, and hydrofluoric acid. If you happen to like to ever work on staining glass and so forth, you probably use some HF. All right. So weak acids, meaning that they don't dissolve 100%, very little. So how do we depict them in a diagram? On the left is an example of a weak acid, okay? And so to show it in the diagram, we may show one pair of ions, okay? And then maybe show about 4 or 5 paired up HF. Notice they're not separated, they're together because the bulk of it is still intact. They didn't break apart very much, just a little bit broke apart, okay? Now, an example of a weak base is this one, MgOH. This is magnesium hydroxide, magnesium hydroxide. Now, when we get to the table of solubility, we will find magnesium hydroxide to be classified as insoluble. Insoluble doesn't mean that it's not 100% insoluble. That just means that very small amount will go in solution. And the rest of it being a solid, being insoluble, will precipitate to the bottom of the container. And that's what's being demonstrated here in this diagram, where the bulk of the magnesium hydroxide is a solid. In fact, if you ever were to put some milk of magnesia in a glass and pour some in a glass and let it sit there, eventually it will separate and the bulk of the white cloudy material will be down at the bottom. Okay, that is your magnesium, I believe, hydroxide compound. And then you'll see a clear solution on top. And so that's what this in the bottom depicts, that the bulk of that magnesium hydroxide will settle to the bottom of the container as a solid. Whereas we still have a little bit of material in solution, okay, shown by the ion. So we only need to show one pair. Remember, there are 2 hydroxides because that's the formula. There's 2 hydroxides for every magnesium ion that there is, okay? So on the left depicts a weak acid, and on the right depicts a weak base. Now, somebody once asked me, well, how come the HF isn't down in the bottom here? Well, HF is the only thing that's down in the bottom as a participant would be ionic compounds. Ionic compounds. Okay. You won't find HF just sitting down there because, first of all, it's a liquid and it's kind of mixed in the solution, so it doesn't fall to the bottom as they precipitate. Okay, so that won't happen there. Case in point would be carbon dioxide. Carbon dioxide is not truly soluble in water. It kind of is dissolved in there, just hanging out. But if you boil, take your soda pop, I shake this up, boom, my carbon dioxide is coming out. If it were truly soluble, I can shake it all day and there'll be no bubbles. All right, let me clear up my mess here. All right, so now some examples of weak acid and weak base are hydrofluoric acid, which is HF, carbonic acid, which you'll find a lot in soda pop, okay? Phosphoric acid, which by the way, you find a lot in soda pop, and acetic acid, which you can find in a bottle of vinegar. That's what it is. The common name of it is vinegar, acetic acid. And then an example of a weak base would be magnesium hydroxide. But again, it'd be any salt hydroxide salt that shows insolubility in water, okay? And that's what we're talking about, it's just the solubility. Now, let's take a look at the following. And it's going to ask you here, which one of these diagrams depict a strong acid? What do you guys think? What do you guys think? I got 4 diagrams. A, exactly. A would definitely demonstrate to be a strong acid. And why is that? Because all the protons are free. There's no example of H8 still intact, as in the case of B and C. Okay. And who knows what D is, but it's basically something that's not an acid because there's no acid here, no hydroxide. So it could be anything. Now, if I needed to compare which one would be stronger, B or C, I would have to say B would be stronger when I compare B and C only, simply because there's more protons in solution compared to C when it shows only 1 proton. So B will be a little bit stronger than C. Both B and C are weak, okay? Remember that. They're weak acids because they're still showing the HA, most of them still intact, and only showing the salts or the ions, very few of them, okay? So B and C will both be weak acids, okay? And B will probably be classified, can be classified as a little bit stronger acid than C, simply because they got more protons. And there's no depiction of any base here. We see no hydroxide occurring here. All right, now that brings us to the pH scale. The scale here is a numerical scale. Okay, just like it is obtained from doing what we call the log. Now you might say, we got to do the log here. Well, okay, you might need to do the log, but on your calculator, you should have a button that says log. And all you do is you push the button. Okay, we'll get to that in a second here. The scale runs from 0 to 14. 7 is what is considered neutral, okay? Anything less than 7, denoted here by the pink, is acidic. And anything greater than 7 is denoted as a basic or alkaline. That's another word used for it. Now, within the acidic and within the scale, it does talk about strongly acidic and weakly acidic. And that's a variable scale. You know, this can vary a little bit, you know, sometimes strong is all the way up to 2, but your stomach is, as pH is somewhere in this region. If you had Drano, not Drano, but liquid plumber, that pH is somewhere in that region, okay? Acetic acid or vinegar, somewhere around 3. And I'll give some examples here in a bit. Okay, now how do they define the pH? Well, it kind of introduces you to these bracketed these brackets. All that is a concentration. We're going to have more on that later on, specifically what exactly it means. But for right now, the bracket just means concentration. So in this scenario, when the concentration of the proton is greater than the concentration of the hydroxide, we're in the acidic area, okay? When the concentration of the hydroxide is greater than the concentration of the proton, we're in the basic area range. And when the concentration of the acid, proton, I should say, equals the concentration of the base, guess what? We're in the neutral domain, okay? Neutral domain. So that's basically how it works, okay? And it is a mathematical function, the pH scale. Clear this out. Of the log of the concentration, specifically what's called the negative log. We'll explain here in a second. All right, so that unit I just mentioned is concentration. We kind of introduced it a little bit too early. You'll mean more later on, but the units for that concentration for right now is what we call moles per liter, volume, moles per liter. We haven't talked about moles. We got a whole section about moles. So for right now, just remember that's the units for concentration. Otherwise known as molarity, which is moles per liter, okay? And what I just talked about is simply what I just explained. When the concentration of the proton is greater than hydroxide, then we have an acidic solution, okay? And vice versa, it is a basic solution. When they're equal, we get a neutral. Clear this up. All right. I got 237. Tell you what, let us stop it here on slide 16. No, chapter 8. Yeah, let's stop it at slide 16.